Rani, Operation Director from GCC International Authority, please come to the stage.
Assalamu alaikum. So good afternoon, ladies and gentlemen, and welcome to session number 2 for today, day 1, session 2, titled Power System and Grid Solution. My name is Hashim Zahrani. I am honored to chair the session. Today, we will explore innovative approaches and key challenges in ensuring resilient, sustainable, and efficient power systems, focusing on gradient resiliency, renewable energy integration, and grid modernization. The session will feature 6 speakers, followed by a panel discussion, and I encourage everyone to participate in the panel discussion. Without further ado, I would like to invite our first speaker, Engineer Frederick from Cedivir. Frederick is a technical assistant engineer with over 13 years of experience in hardware and insulator testing, particularly in the testing and simulation of insulator units for overhead transmission lines. He is an active member of SIGRI B2 committee. Frederick holds an engineering diploma and a master's degree from École Centrale in France, with a title, Enhancing Grid Resiliency with a Robust Insulation in Severe Environmental Condition. Frederick, the floor is yours.
So good afternoon, ladies and gentlemen. I'm very pleased to make you this presentation. This presentation will deal about insulation systems to enhance the resiliency of power grids in severe environmental conditions. And it will focus on overhead transmission lines. Thank you. So a few words about the context. How do we characterize the resiliency of insulators used on overhead transmission line? First, it is the capacity to ensure electrical insulation, whatever the circumstances, like meteorological condition and polluted environment. And this presentation will focus on polluted environment. Second, the insulator shall show in service the most reduced or limited aging over time. And third, the insulator shall show the lowest risk of failure. Failure due to electrical flashover, due to pollution, or even failure, complete line drop to a failure of the insulator. And this shall be true for both AC lines and HVDC lines. For DC lines, pollution is much more harmful and severe than on AC line, and pollution becomes the most predominant phenomenon to consider. So to mitigate the effect of pollution, a good solution is to use HTM materials. HTM meaning hydrophobic transfer material. It is now well known that HTM surfaces are favored to reduce the risk of flashover induced by pollution. However, silicone is an ideal material, but aging can degrade the integrity of the insulator surface. Polymer housing of polymer insulators are known today to be at risk of erosion resulting from pollution-related corona and dry bond activity, leading to possible severe failure and line drops. Adding a silicone coating on the surface of a glass insulator was defined as the optimum approach to combine the pollution performance of polymer insulator and the resiliency and reliability of toughened glass insulators. RTV coating on glass and porcelain insulators is no longer considered as a marginal approach, but is clearly part of the design of new transmission lines, especially in this region of the world. The major push came from the decision taken more than 20 years ago to have a product coated in a factory with an industrial process in controlled conditions rather than in the field where the difficulty of uncontrolled outdoor conditions can compromise the long-term performance of the product. As an illustration of this growing demand, the graph shows the actual trend seen by Cediver in the development of silicone-coated glass insulators. These numbers are based on our experience, and they show growth of 30 times over a period of approximately 20 years. The big interest for this kind of product is the ability to give to glass insulators the pollution performance of polymer insulator without the risk inherent to polymer. The main advantages of factory-coated insulators are consistency of quality, lower risk of quality issues, either in thickness, coverage, and adherence on the glass surface. The product is no longer defined as a coating, but as a factory coating resulting from the association of an insulator itself, a silicone coating material, and an application process, and the whole being under the responsibility of the insulator manufacturer. Here are some examples of quality defect observed on lines and on insulators that were not coated in a factory, where you may have some inconsistent thickness and lack of adherence. To evaluate the performance of this factory-coated insulator, it's important to talk about testing and standardization. The need for clear and well-defined material and testing specification led to the work being done by the IEC 36 Technical Committee. The outcome of this work is the upcoming IEC 63432 standard for RTV-coated insulators, which publication is expected by next year. And the work of this IEC committee is based on the previous work of the CIGRE, who published two very interesting documents, the technical brochure 837 and 838. It is today understood that the aging process of silicone material comes with several changes in the properties of the material. Loss of hydrophobicity will progressively let the leakage currents increase and subsequently start an erosion process. This has led to numerous attempts to define an erosion test. The various options available for evaluating the aging of silicone coatings on glass or porcelain insulators were the following. First, the 1000 SAL fog test described in the IEC 62217. This test depends largely on the USCD, what we call the Unified Specific Creep Resistance that is being used, and on the insulator profile. The second test is the 5,000-hour multiple stress test described in the IEC 62730. But both tests are designed for polymer insulators, which have a sheet of minimum 3 mm in thickness required to protect the core. But these tests are not designed to discriminate the performance of coatings, which are applied in thin layers, typically less than 0.5 mm. But the 2,000-hour multi-stress test is today and by far the most frequently used and will most likely be included in the upcoming IEC standard. It is not a reduction of the 5,000-hour test, but follows a different protocol as shown here. The test combines periods of exposure to SAL fog, clean fog, artificial rain, solar radiation, periods of drying, and periods of energization. The acceptance criteria of the test are the following: not more than 3 flashovers, no tracking, and the erosion shall not reach the dielectric surface of the insulator. This picture shows different test result as a function of the chemistry and the application process of the coating, noted A to D. As you can see, this test has proven to be effective in discriminating coatings prone to erosion, like C and D, compared to good survivors like A or even B, under the given stress condition. As I said previously, HVDC is a special case. So we at CEDIVER has adapted this 2,000-hour multi-stress to DC condition. Basically, the test arrangement is the same, but energization is made through a DC voltage source. Pictures on the right show comparatively results of tests performed in both AC condition on the top and in DC condition at the bottom, on the same insulators, but with two different coatings. Coating 1 on the right, and CEDIVER coating named SEDCO on the left. As you can see in AC condition, the two coatings do not show any erosion and pass the test. However, when you make the same test in DC condition, coating 1 shows significant erosion and does not pass the test, whereas SEDCO coating is in good condition. So this demonstrates that the 2,000-hour multi-stress test is also effective in discriminating coatings when used in DC conditions. And coating quality required for DC application shall be much higher than the one required for AC application. An important parameter to consider is the estimation of the end of life of these coatings. In service, silicon insulators may suffer from significant degradation over time when they are exposed to severe environmental conditions. Corona effect, and in particular the water drop-induced corona effect, is the most harmful phenomenon for composite insulator, which can result in a complete line drop when the degradation reaches the fiber core of the insulator, as you can see on the bottom left. For silicon-coated insulator, the electrical activity can cause cracking and erosion of the coating, creating hot spots locally on the surface. And when this erosion reaches the glass surface, the heat induced can lead to what we call the shattering of the glass disc. However, the remaining insulator that we call a stub is safe and keeps sufficient mechanical strength to avoid the line drop. So an interesting test to reproduce this phenomena on coated insulator is the tracking and erosion wheel test defined in the IC 62730. This test has been used for polymer insulator with the aim of defining the ability of housing material to sustain strong regular dry bond arcing. But it can be used as well for coated glass or porcelain insulator. Here are some examples of tests performed for investigation purpose on either porcelain or glass insulators with the same features and with two different coating chemistries, noted A and B. You can see that on the left, coating A exhibits loss of adherence after the test, whereas coating B does not show any damage. The development of dry bond arcing over time intensifies as the hydrophobicity is being lost or reduced. The behavior on the top surface of the insulator is strongly influenced by the assembly of the cap on the dielectric surface. A gap between the base of the cap and the upper surface of porcelain insulator will promote discharge activity, leading progressively to severe erosion and whatever the type of silicon. This phenomenon is less prone to occur when the cap is sealed on the glass disc as per CEDIVER design. The bottom sides of the insulator are typically more impacted given the concentration of electrical activity around the pin. This is where the nature of the silicon itself can make a difference, where you can see here example of two coatings A and B applied on the same insulators Coating A, after 28,000 cycles, there is a complete destruction of the insulator. Whereas after 65,000 cycles, when we stopped the test, coating B was still sound and safe. It seemed also that while all samples were coated with similar care of adhesion, porcelain is more inclined to lose adherence than glass. Oh, sorry, I made a mistake. The same difference in the behavior of the coating is also observed on the porcelain insulators. Type A, puncture of the porcelain after 8 to 14,000 cycles, whereas after 30,000 cycles, coating type B is still in good condition. So it seems also that while all samples were coated with similar care and of adhesion, porcelain is more inclined to lose adherence than glass. And this is most probably due to the shape and the design of the insulator wreath underneath. So even if this test is not used at this point in any standard for silicone coating insulators, the outcome should be considered with interest. The test is relatively rapid and not too complex to put in place, and it appears to provide the following elements. Ability to survive strong electric activity can be discriminated. A ranking of coatings performance can be established, and adherence recovery can be demonstrated in this test. To conclude, I would like to remind the following key points to keep in mind. Silicone coating is a fast-developing technology. IEC is developing a standard for RTV coated insulator, which will be the key for the future. All coatings are not equal in performance and aging. 2,000-hour multi-stress is a good test for aging evaluation. End of life can be approached with a tracking wheel test showing good correlation with end of life in the field. All coatings do not provide the same longevity. Unlike polymer, but also porcelain insulators, end of life of coated glass insulator remains safe with stubs which not only are a good visual indicator, but remain safe in service. Coatings which work in AC do not all age equally in DC. The 2,000-hour DC test provides further discrimination among candidates. Thank you for your attention.
Thank you, Frederick, for your excellent and fruitful presentation. That was an excellent details of insulators and comparison between porcelain and glass insulators. Now, our second speaker will be Engineer Abdullah Al-Habsi. Engineer Abdullah is the System Studies Section Head of Oman of OETC. Since 2015, he has specialized in power system studies, including network reinforcement and renewable integration. Abdullah holds a bachelor degree and a master degree in renewable energy from Sultan Qaboos University, and he will be presenting transmission upgrade to support Oman energy transition. Abdullah, all the best. The floor is yours. Good luck.
Assalamu alaikum jami'an. Good afternoon. Today I will talk about the transmission upgrade to support Oman energy transition. The main investment in transmission toward increase of renewable energy in the system. Yeah, no working. As you know, worldwide that the climate change in the worldwide have more intention in world. And there is a need, many of utilities that need to integrate a lot of renewable energy in transmission system and power utility. So integrating of a lot of renewable energy, wind, solar, and other renewable energy will introduce another challenges in terms of power stability system. Having a lot of renewable energy integration to the transmission system will introduce challenges in terms of voltage support, in terms of frequency support, in terms of short circuit level at transmission system, and also a reduction in inertia. All of that will have impact in transmission system, in voltage stability and frequency stability, where reducing the inertia in the system by replacing the existing conventional machine via renewable energy will decrease the inertia and increase the rate of change of frequency at the system. A lot of initiative need to be taken in consideration for the future to integrate a high share of renewable energy. As Oman have a target to reach 30% of renewable energy in 2030 and 40% of 2040, and having a mix of generation from wind, solar, and other renewable energy, a lot of challenges becomes very essential to be taken in consideration for planning and system integration and expansion next years. As you know, that we have three classification of integration of renewable energy, where we have, if the renewable energy share is almost from 0 to 20% or 25%, the existing grids can withstand with a small change in and modification in the system. If we have increased that renewable energy share up to 50%, there is a high change in terms of voltage support, in terms of frequency support to the system. Having more 50% in the system will have a big impact in system stability, where a lot of changes should be made in terms of short circuit ratio and reserve for the system and the stability margin of the system. So now I will go through the main challenges that will happen if we have high penetration of renewable energy. Oman has interconnected with GCCIA through network 220 kV system from UAE, and NER will be upgraded above to 400 kV. This integration, due to all the Gulf targeting to have renewable energy in their system, a high impedance of interconnection between Oman and other GCCIA will introduce an oscillation, an intermediate oscillation that need to be captured and need to have a proper solution in order to dam that oscillation. Another one is related to a need of smart or fact devices, where that need to be implemented in the system to support the system in voltage stability. Another one, we have an energy mix impact. Having a lot of renewable energy will decrease the system inertia, and also have a voltage response according to the short circuit ratio from different perspective. Having also a large scale of renewable energy will introduce an issue related to the nadir frequency and rate of change of frequency. So a major integration of renewable energy may a challenge in terms of system planning and control also. One main element also to measure the system strength, it is the short circuit ratio. And that ratio, if the short circuit ratio at the connection point of renewable energy more than 3, it means that the voltage and frequency does not change easily. So that will give you an indication that we can integrate renewable energy into that connection point. However, having less than 3% or 3 short circuit ratio, it means that the grid is weak and cannot be integrated a lot of renewable energy at that connection point. So we need to have to strengthen the system, either to have a generation of conventional to increase the short circuit. Another issue related to the transmission system, we can eliminate all these risks by having a lot of integration and a lot of investment in transmission system. But this is not a case. We need to have an optimal cost for transmission as well as the operation, as well as the constraint in the system. So we need to invest in an optimal way. Oman start to enable that integration of renewable energy, having different project where we have the first phase of interconnection between north and south, and the second phase with from north to south, which is almost the first phase 400 or 500 kilometer, the second phase 600 kilometer. Oman have a more potential for solar, which is mainly can be integrated to RAPT 1 and RAPT 2 project. Another initiative from transmission point of view, OETC try to integrate the rural area, which has mainly depended in the diesel generator, and different connection has been made and will be made in the coming year. We have Msira will be connected via submarine cable from Mahout. We have Shahba Saib, Modi, Mazyuna in Salala. We have Sih al Khairat. We have Srab. We have Uwafi and other grid stations that will be replaced the diesel generator and support Oman for the next for the net zero target. Another initiative from the transmission point of view, we have integration a lot of renewable energy project since 2019. First wind farm, which is 50 megawatt. In 2021, we have every 560 megawatt integrated in every area. In 2024, we have 1,000 megawatt already in service and contribution to the system energy. In 2027, we have a mix of wind and solars power plant. Almost we have near 2,000 megawatt. In 2028, we have 2.2 gigawatt will be integrated to the system, mixed of wind and solar. And in 2029, we have almost 1 gigawatt from wind power plant, Duqm 3, Shlim, Al Ghazar. So the RAPT 1 and RAPT 2 will integrate all this renewable energy. Mainly the renewable energy come in that area. To accommodate that much of renewable energy, we need to have some flexible unit. And one of that solution is to maintain the battery storage at transmission system, where we have for the coming years almost 1 gigawatt integrated to the system in different grid connection. This is the primarily assessment that indicate the location and the size of needed of battery storage. In conclusion, there is a need to integrate a lot of renewable energy. However, we need to maintain the system stability. And in order to maintain the system stability, we need to have interconnection with existing and future international interconnection with the GCCIA, with Iran, with Yemen, and India. We need to make sure that all the renewable energy should maintain the voltage regulation and operate as a voltage control at a voltage control mode. We need also to ensure that also to have some operational measures that to introduce to have under frequency load shedding, under voltage load shedding to maintain the system stability. And having also tuning the existing power system stabilizer in order to maintain the system security. And we need to get benefit from wide area monitoring system, so we need to address all the phenomena and events that happens due to the having a high rate of having a lot of renewable energy in the background. That's all. Thank you so much for listening.
Thank you, Abdullah, for your excellent presentation and sharing your expertise and insights in this important subject for the future of grid of Oman. So without further ado, we'll go to next speaker, Engineer Abhishek Kar. Mr. Kar is the Head of Strategy and Sustainability at Siemens Middle East. With over a decade of experience, he has led initiative on smart grid, microgrids, renewable energy, and decarbonization strategies across Middle East. He holds MBA in Finance and Operation and Bachelor degree in Electrical Engineering. Mr. Kar, the floor is yours. Good luck.
Thank you so much for this introduction. An interesting topic, but let me start with scoping the magnitude of problem that we are talking about. Renewable energy. An estimation by IEA says that approximately 3,000 gigawatt of energy is waiting to be connected in the grid, irrespective of being ready to be connected. Now, just for an approximation, how much is this 3,000 gigawatt? This is approximately 5 times of the total solar and wind which was actually generated in 2022. Now think about the problem and what is the term which was given to this entire problem? We call it gridlock. So we have the renewable energy ready for us, but are we ready to connect it to the grid? And that is the magnitude of challenge we are talking about. So thank you, Mr. Abdullah, for explaining the complexities and the requirements of a renewable integration. And you rightly touched upon the part, mostly on the transmission side. That makes my job a little easy. I will be talking maybe on the distribution side a little bit. Let's start with it. Where did the journey start of renewables? We started with talking about net zero. So it's about getting rid of the renewables, getting rid of the non-renewables, and on the other end, also electrifying our operations. Anything that we do, our vehicles, our industries, our buildings, and this entire thing was happening on a platform which is our grid. Now this infrastructure, let me remind you, was built a decade back. It was not ready for such a massive and such a fast change. So we are talking about a grid which was not ready for it, but it has now been asked to take care of our net zero initiatives. So an estimation says that almost half of the entire grid has to be either replaced or retrofitted, and a grid length has to be doubled over a period of time to achieve this net zero scenario. So this is the challenge that we are talking about, and this is where the role of renewables, which is supposed to be approximately 90% of our supply in future, is going to come into. The leadership in Oman also has very ambitious vision. We just saw in our last slide how the peak power is going to escalate with this ambition of increasing our renewable share here. And almost most of the projects are already in place which are working towards it. That brings me back to the same question, are our grids ready? So let me start with understanding what we can actually do and how we scope and how we design a solution to this problem. First thing first, what was the grid that was designed for? It was a static grid, a grid which connected the supply side to the load side. The grid was supposed to stay there and just be a connection between the two ends. But look at us now. We are talking first a stochastic supply side, a supply which is varying during the day, during the night, during seasons. And Like Mr. Abdullah said, there is oscillation, there is frequency issues, the voltage fluctuations. Everything has to be considered while redesigning this grid. That is one part of the problem. The second part, we had a passive customer base, a customer who was just using it for their own usage. But now look at us. We have a consumer base where we are adding rooftop solars. So the power is not just getting taken out, it is also getting added to the grid. We are having flexible electric vehicles getting charged from the same consumer end. So all this turbulence is requiring a grid which we call an adaptive grid. The grid has to transition based on the challenges. And of course, the challenges were already mentioned, but I just listed them that there are so many challenges, but let us look at it from three perspectives. We call it the trilemma of utility operators. First is definitely going renewable. First is definitely achieving the climate impact. Second is the cost. We need to have the electricity in an affordable and a usable format. And the third leg of this trilemma is definitely the stability. Now, balancing all these three things, the utilities are in a very tragic and a very important, decisive turning point. And the biggest challenge is we are trying to fix a roof while the sun is shining. So the grid is already operational, and we have to retrofit it or upgrade it so that we can mitigate all these challenges. Now, the question is, how do we do this? Is there a solution to it? Well, the solution is there, but it's not that simple. We are talking about a grid which is a very balanced, interconnected system, right from the transmission to the substations, to the consumer end, to the distribution, everything is interlinked. If you look at this complicated picture, it shows how many different technologies goes into managing a grid. You can see in the transmission end, there are FACTS, HVDCs which are being implemented. You can walk through the entire system and end towards the consumer end, where we are talking about advanced distribution management systems. And to add to it, the advent of AI, both as a help as well as maybe a challenge to the grid. So how do we start with this thing? The solution is not a single solution that fits everyone. You have to start with thinking how first we modernize. Second, we have to talk about our readiness for digitalization, for incorporating those technologies which can help us achieve this renewable integration. And then we have to think from a very integrated perspective. We have to think about all the moving parts in the grid which can come together and help us achieve these changes. So that's a thought which goes about how do we manage this complexity of grids, being ready for the future. Now, the transmission part was well explained by Mr. Abdullah, but let me show you what we feel about the conventional grid. In spite of this upgradation of grid infrastructure, we still feel that there will be a huge gap, which will be a gap for the hosting capacity. And the question is, how do we mitigate or how do we address this challenge? So the issues are already visible. Most of us who are working with the utilities, we understand the biggest thing that is keeping you awake at nights is the inertia problems, the problem of inverter dominance, the problem of grid interconnection, also the problem of proximity. So now the supply source is not sitting outside the town or outside the city. It is sitting in the top of your building. And this proximity is also causing a huge challenge for a distribution grid, which, to be honest, we are hardly visible of what it is happening there. We see that only 5% of our lower end distribution grid has a digital visibility. We know what is happening there. Most of the grids are not even enabled with sensors or digitalization to help us understand. So with these complexities, the way we are designing and we are operating the grid has to be redesigned. So we had a grid which was designed for top-down operations. We had a control room and we used to think, how do we manage the grid from their perspective? But the paradigm has shifted. Now we have to think of a bottom-up approach. How do we start thinking on the distribution level, start giving solutions right from bottom and start planning up till the top? So this is the change that we are talking about in terms of our distribution and our grid planning. And of course, the biggest enabler that we see for the future is digitalization. The hardware, the solutions, they have to come together to enable this digitalization, which can help us achieve a grid which can support this renewable integration. Right. So just considering the time limitation, let us talk about the evolution of grid. We started with a grid which was a copper plate technology. So we are talking about cables, transmission lines, and other things. Then we evolved into a grid which was called a grid automation era, where we are talking about smart grids, solutions, smarter indices, everything that helps us operate this grid. And then we are visualizing a grid which is supposed to be an autonomous grid. Now, in place of actually explaining what autonomous grid, what I will do, I will play a small video to show you how an autonomous grid of the future is actually a possibility as well as a requirement for our grids to think about this distributed energy resources in future. So that's my time, and I want you to live with this thought that the vision and the future is a grid which can be smart, intelligent, and maybe an autonomous grid, but the journey starts today, and we are all in it together. So thank you so much. This is Abhishek. Thank you for your patient listening.
Thank you, Abhishek, for your excellent presentation and video also. Our next speaker is Engineer Kalyan Tata, presenting the dynamic reactive power compensation with variable shunt reactors. Engineer Tata is an application engineer at Hitachi Energy, India Limited, and focusing on power distribution transformers, reactors, and reactive power system. He has over 15 years of experience working on design, project management, and sales function for transformer components. All the best.
Thank you for the introduction. So, good afternoon, ladies and gentlemen, and thanks for being here. I'm very excited to take you through today's topic, that is dynamic reactive power compensation using a variable shunt reactor. So before we dive into the main topic, let's have a brief overview of the agenda. First, we will emphasize on the overall structure of the power network and the different technologies available which can support the stability of the grid. Next, we will explore what is a reactive power compensation and how it is important to maintain the different voltages at different nodes of the power system. Later, we will try to understand how the dynamic reactive power compensation is possible using simple techniques like variable shunt reactors. And finally, we will try to understand the basic design and construction of a shunt reactor, both static as well as dynamic shunt reactor. So these slides give you an overview of the power system right from generation, transmission up to the utilization. On the left-hand side, you can see the different sources. The different sources of generation that can be conventional like coal or nuclear. And we have even the renewable sources like solar and wind. So it's important to note down that whenever you are having a large-scale renewable integration, they are very good from the sustainability point of view, but they induce some kind of challenges for voltage stability during the grid. Then we have the transmission line in the center, which is like a backbone of the entire power system, which is transmitting power over a long distance. It can be through HVAC or HVDC, or HVAC is an important topic for today because we will be discussing the reactive power compensation in high voltage alternating current lines. And then we have the load center. It can be industrial customers who demand for reactive power. It can be large scale commercial complex. It can be residential load centers. So here, what is a reactive power and why the compensation of a reactive power is required? On the right-hand side, you can see we have this power triangle where the active power is the total power supplied to the system. Active power is the power which actually does the actual work in the system. And then we have the reactive power. So reactive power is not something that does the actual work, but it is very important to create magnetic fields, to maintain grid stability, to maintain voltage across the grid. And here we have shown the diagram of a very long transmission line. So the transmission line is having interaction with the ground, and with this interaction, it forms a virtual capacitor body. And this capacitor body is indirectly inducing the reactive power in the system. And this reactive power is increasing the voltage with the help of the Parenti effect, which we all know. On the contrary, we have the inductor load like the shunt reactors, which will consume the reactive power and will bring back the voltage level to normalcy. Now we can discuss the voltage profiles under different demands for reactive power. Again, we have a single line diagram of this power network. We have the infinite bus, we have the transformer, transmission line with the capacitance. And here, the Q1 is the total reactive power getting induced in the transmission lines. So under normal circumstances, the total reactive power generated by the system and the total reactive power consumed by the industrial load, Q2, will be constant. And then we have the voltage from the sending end, that is V1, and the voltage which is received at the consumer level, V2, will be constant because we don't have any reactive power unbalance. But imagine a situation when you have a group or when the demand from the industrial customers will drop down, where in such a scenario, you will have more reactive power generated in the system than it is consumed by the customers. In that condition, due to Parenti effect, we will have a very high increase in the voltage at the receiving end. And this can put the insulation under stress. Many equipment can get damaged, which we don't want. One of the easiest solutions to compensate the imbalance between the reactive power is to have a shunt reactor connected very close to the load centers. And this shunt reactor is consuming a part of this reactive power which is generated by the system. So here, the total reactive power generated in the system is partially consumed by the shunt reactor plus the industrial load. And again, in this static compensation scenario, we have the total voltage between the sending and the receiving end constant because the total power we are able to balance using a shunt reactor. But when we talk about the actual scenarios in a power network, the requirement of different industrial customers is not constant. It keep on varying during the different loads. And when consider a situation when you have the shunt reactor connected to a system and the load, the demand for the reactive power by the industrial customers even also increases. In this scenario, what will happen? The shunt reactor is overcompensating the network so that the total reactive power generated in the system is less, wherever the total demand by the industrial customer plus the shunt reactor is more. So what will happen? You will have less voltage at the consumer level, which will make the equipment working there to not working as per the satisfactory level because it's not getting the total voltage it's required for. The easy solution is we can think that, okay, when we have this imbalance or overcompensation, we can simply remove the shunt reactor out of the network. But this calls for two different challenges. One, you need to have a complex network system. You need to have bigger circuit breakers which can disconnect the shunt reactor. And second, most important is while you're disconnecting a reactor of significant MVR from the network, you're actually creating a turbulence or transients in the network because you are creating a big imbalance with a sudden disconnection of the circuit breakers. An optimum solution will be to have a reactor which can induce variable reactance or which can absorb variable capacitor reactance from the system. So whenever there is a change in the load dynamically, this reactor should be capable of dynamically absorbing the power as per the demand or as per the voltage level instability we can sense from the transmission lines. So under this condition, again, even when we have dynamical demand from the customers, a variable shunt reactor can absorb dynamic reactive power from the network. Now, what is a reactor? So, in simple terms, if you define a reactor, it's a simple coil which is wound across an air core or some gap core construction, and it has a major functions. That is, normally we have a shunt reactor or a series reactor. So, whenever you are connecting the reactor in the shunt, like from line to ground, is absorbs capacitor reactive power. The another function of a reactor, when you connect with series, it increases the system impedance. So you can increase the system impedance to limit the fault current, or when you're connecting through a neutral grounding reactor, it can limit the unbalance or the neutral grounding current through its higher impedance. So these are the two different functions depending upon the position of the reactor in the system, either in series or a shunt mode. Now coming to the construction, it's similar to a transformer, where you have a winding and a core. The only difference is normally in transformer we have a multi-winding because it works on the principle of mutual induction through electromagneticity. And then we have a very high permeable core. In the reactor we do the opposite. We have the core with very high reluctance. So we want to reduce the permeability of the core. And second most important is when we have this higher air gaps in the core, like you can see, these are few air gaps in the core which we are constructing from. So these air gaps are important to maintain the high reluctance of the reactor, which is the desired function of this shunt reactor. And these air gaps can absorb the reactive power from the system. Of course, when you are building a core with very high reluctance, there are some challenges that their no-load losses are higher. It has a lot of vibration and noise challenges. So this is something that has to be taken care while manufacturing a reactor. Than a transformer. The transformer is relatively simple in construction compared to a reactor because it doesn't face so much of these vibration and noise challenges. Now, what is variable shunt reactor? So, variable shunt reactor is simple. It's a reactor with an on-dot tap changer. So, it has a tap changer connected to its winding. It keep on changing the number of turns with a smooth flow of inductance. Like whenever you have a higher demand of higher inductance, it can add a number of turns without creating much transients in the system. So it's creating a variable inductance, and when this inductance reacts with the frequency of the the transmission line, you get variable reactance. So without creating much turbulences or transients in the system, variable shunt react by the help of an on-dot tap changer can create or can absorb time variable reactive power from the system. Now this slide talks about the feasibility range of a shunt reactor, on how much modification, how much adjustment we can do to a shunt reactor. The graph shown here, it shows that across the different voltages and the total demand for reactive power, how much adjustment is possible. So you can see when you have a shunt reactor of very high voltage coming to 550 kV, you have almost 50% variable range. Yeah. And when it comes to low voltage, say for example 100 kV, you have almost 70-75% of the adjustment. So this adjustment or this variance is not a function of the reactor or not a limitation of the reactor, but it's mainly decided by the on-dot tap changer, which varies the number of turns of a reactor. So on-dot tap changer has some limitations, like it has a fixed number of turns, it has a specific step voltage, it has specific transient stresses, specific leakage inductance. So these limitations of the OLTC are deciding the different variation possible with a variable shunt reactor. So the final takeaways, we have seen that voltage, whenever you have, you need a dynamic absorption of the reactive power from the power system, it can be done by using a shunt reactor equipped with the OLTC, which can fine tune the number of turns, and it can simply keep on absorbing depending upon the load, depending upon the reactive power generated and whatever reactive power being consumed by the dynamically varying load. Then we have the variable shunt reactor that is connected anytime to the system, no need to disconnect it and create any turbulence. And this is very important when you have large scale integration of renewables. So with the variable nature of the shunt reactor, you have more confidence or more flexibility to integrate more and more renewables in the system. Then when it comes to VSR, that variable shunt reactor, you do need to have a very complex structure of breakers and a large transmission substation which demand for capital investment, because here just with a reactor and a tap changer, you are able to generate equipment which can flexible enough to adjust itself to the flexible requirements of the transmission system. And last but not the least, especially that variable shunt reactor not just compensates the reactive power, but even it's flexible to absorb or maintain voltages when there is a demand from different weathers. Like in most of the countries, there is a demand in power varies from summer to winter. So even in those conditions, VSR can maintain the voltage level. And most important of this flexibility in nature, like it can adjust itself to the output demand. We can place a variable shunt reactor to different nodes or different positions within a power system, making it more and more flexible from the investment point of view or from the installation point of view. So that's all from my side. Thank you for listening.
Thank you, Kalyan. You did a great presentation. Our next speaker is Dr. Maximilian, presenting an interesting subject, underground cable versus overhead lines, a sustainable solution for future grid. Dr. Maximilian is a project manager at Train Mainlink with a PhD from University of Bremen, with an extensive experience in geotechnical and large infrastructure projects. Alongside him will be engineer Timo, who is the branch manager director at Fisher, with a background in civil engineering and project management. All the best, Dr. Zin. Okay. Thank you.
Thank you very much for the opportunity to speak at these Power Talks. Today we like to talk about power transmission, underground cable versus overhead lines, a sustainable solution for future grids. At the beginning, we like to introduce ourselves. Later on, we like to talk about the transmission of the national grids. Further on, we're going on with the underground tables, technical benefits, and at the end, we take an outlook on the partnerships. Our perspective on the Oman Vision 2014 places a particular emphasis on the role and significance of underground cables within the framework of national development strategies. We view underground cables not only as technology infrastructure, but as an integral part of sustainable energy supply and the modernization of the electrical grid in Oman. In context of Vision 2014, which aims the economical diversification, ecological sustainability, and social development, we see the increase of use of underground cables as a promising opportunity to make a transmission more effective, safer, and more environment-friendly. Our analysis take place into the realization of the Oman long-term goals. Who we are? We are a consortium consisting out of 4 specialized German engineering companies: GPM, Fischer Teamplan, Mailänder Consult, and Ingenieurbüro Berger Partner GmbH. Together, we combine our expertise to implement complex projects, efficiencies, and sustainabilities. Our team consists out of 900 employees, including engineers, environmental assessories, geologists, and technicians. With over 16 years of experience in pipeline construction, both open-cut and trenchless methods, we offer comprehensive services, from conceptual planning to construction supervision.
We specialize in crossing various infrastructure, such as railway systems, roads, and waterways. Furthermore, we conduct throughout underground investigation and provide expert advice in the field of geotechnics. International projects we have done with water reservoir, phase 4, 5, and 6 in Dubai, completing 2011, the photo on the left. On the outstrike of Dubai, one of the world's largest drinking water reservoirs was constructed. The Dubai Electricity and Water Authority invested around $100 million in the construction of 3 new tanks with a total capacity of 800 million liters of drinking water. The reservoir supplied with water from the distant plant located approximately 35 kilometers away in Jebel Ali area. The new facility is of central importance for the reliable water supply of the neighboring district of Dubai. Another completed project in the Middle East is the Sunset Majlis. In Dubai, realized in 2016, the client was the Engineering Office of Dubai, which managed the prestigious undertaking based on unique concept design in detailed drawings. The Sunset Majlis itself consists of 314 square meter circular structure. The Majlis was constructed on reclaimed land in the sea, is surrounded by a stone embankment and rests on the interconnected foundation system. As well, we're talking about international projects as we are referring to the field of underground cable routes. Currently, Teamplan is involved in 3 significant projects of this area for underground cables. The Anod underground cable route represents a key infrastructure project of the transmission system operator Embryon. With a length of around 300 kilometers, it serves to transport wind power from the North Sea coast to the Rhineland, as shown on the slide left on the top. The route runs in 2 parallel trenches, which each side carrying 2 high-voltage cables. The installation is mostly carried out using open construction methods at a depth of around 2 meters. To stabilize and protect the cable protection pipes, liquid soil is used, often made from locally excavated material. These construction methods ensures high operational reliability. In the event of a fault, one of the 2 lines can be repaired while the other continues to transmit electricity. Those systems provide important redundancy. As the future illustration of the slide shows, the open construction method is not the optional solution in this case. In particular, when crossing underbodies of water or roads within underground cables, the closed construction method, despite higher costs and longer construction times, offers clearly advantage in the case of space for the constructions. Side-up is only required at the start and end point of the route. Various methods are available for implementation, including pilot tube checking, horizontal directional drilling, and microtunneling. The choice of the appropriate method largely depends on local geology and the length of the route installed. Completion of the line is planned for 2027. From that point, the route will reliably supply electricity to around 2 million people in Germany. This project exemplifies modern efficiency and environmental consistent underground cable systems for the integration renewable engineers in Germany. FBGM continues to be involved in 2 additional underground cable projects, the Rhine-Main Link and the SuedLink. Both routes are among the most significant initiatives of German Energiewende, with completion planned by the year 2033. In totally approximately 1,300 kilometers of high-voltage direct current cables will be laid connecting the wind-rich knots, including the Scandinavia area and offshore wind farms, with the energy-intensive south of Germany. The approximately project value lies by around 30 billion euros. In the next slide, my colleague Dr. Maximilian will present the understanding of the mission of 2014.
Thanks, Timo. Also, good afternoon from my side. let's have now a little bit closer look on Oman's Vision 2040, and more precisely on which topics of the Oman Vision underground cables have an impact on. There's grid expansion and modernization, renewable energy integration, green hydrogen integration, grid stability and reliability, infrastructure for new projects. And these mentioned goals of Oman's vision can all be achieved and improved, by our opinion, by considering underground cables as a major transportation system. For this, however, you need to transform the national grid, and how this is done and planned in Germany, I will show you on the next slide. Here we have Germany on the right-hand side, and in Germany we have the Energiewende, as Timo already mentioned. It's energy turnaround. It's a national program or a politically driven agency to transform our energy grids to renewable energies. For this, the national grid is to be transformed from fossil to renewable energies, and partly from overhead lines to underground cables. As already outlined, for these challenges in Germany we have, there is a lot of wind in the north, which is, laser pointer doesn't work. You see in the north of Germany there's a lot of wind in the coastal areas, and we have a lot of energy-intensive industry in the south. So there's this problem that we need the energy in the south, and it's mainly produced and generated in the north. So we have a lot of large-scale underground cable projects to overcome this distance in the first hand, and secondly, to provide the energy in the south, and these cables can transport up to 8 gigawatts of energy per project to where it is consumed in the future. So, and FBGM, our team plan consortium, is part of these large-scale underground cable projects, and just a few points, what complexities and challenges we have to cope with are a lot of regulation and complexities due to the legal framework in Germany. We have a very diverse geology, like in Oman, and for me as a geologist it's always tricky to find suitable solutions. And of course there's a lot of special construction methods like HDD drilling or microtunneling to overcome obstacles. And very importantly, we consider infrastructure, cultural heritage areas and protected areas, and groundwater, for instance. So here I outline one of the major facts which are advantages for underground cables. First, underground power cables are entirely independent of the type of energy, so fossil or renewable. It works both. They provide a higher safety in terms of net stability and less outages. This again prevents costs at supplying these outages. They are virtually independent of the weather and weather phenomena like dust storms, floods, etc. This again reduces costs. Again, another advantage is that they are less vulnerable against physical attacks like vandalism, terrorist attacks, road collisions. They have a lower maintenance and repairing costs. That is an advantage in terms of cost in general. So overhead lines are often less expensive initially, but in the long run, underground cables are often less expensive then. And finally, very importantly, you can protect by underground cable certain protected areas like cultural, archaeological sites and environmentally protected areas. And finally, less electromagnetic disturbances can be inferred, like you see in the top left picture where this airstrip is very close to the underground cables running close by. To sum it up, underground cables have an asset against overhead lines if considering it in the long run, and if you take into account adjacent aspects also. So this is my last slide. As I outlined before, FBGM provides a vital technical and interdisciplinary team with expertise in this field and can be a good partner for Oman's Vision 2040. Underground cables have immense potential to make Oman future-proof and resilient. And as a further step, we are willing to initiate a subsidiary in Oman. And we are also very happy to collaborate in terms of knowledge exchange and university collaborations. And we are also very happy to offer internships in our team. Thanks for your attention. These are our context, and see you around for fruitful discussions, hopefully.
Thank you both for your excellent presentations. So our last speaker is Dr. Ali Al-Kandani. Dr. Ali is the head of Power System Studies at Monenco Engineering with over 12 years of experience. He specialized in system planning, stability analysis, and renewable integration, and of course electricity market. He held PhD in electrical engineering and published a lot of papers on market mechanism and grid stability. Dr. Ali will be presenting the energy storage solution and grid balancing. Dr. Ali, floor is yours.
Hi everyone, nice to see you. I'm here from Monenco Consulting Engineer and hope to have a good presentation, fruitful presentation about the effect of energy storage on grid balancing. Due to the global policy for carbon reduction, there is a lot of renewable expansion in different countries. That means increased penetration of renewable, as all the speakers talk about this. But this increased penetration of renewable faces power system network with new challenges. The first challenge is price volatility, and the second one is grid instability. Price volatility will be happen due to the uncertainty in renewable generation, and also grid instability will be happen due to the reduced inertia of power network and considering renewable in power network. To resolve this issue, one of the solutions is using of energy storage in network that will resolve this issue, but considering energy storage will faces power system with new challenge, that we are talking about this challenge today. There is a lot of benefits comprised from energy storage that can be considered besides renewable energy, considering for end user consumer, also delay infrastructure investment in transmission and distribution, also black start capability, but the main benefit of this energy storage will be comprised from market and economic application, and also grid reliability and increasing frequency stability of power systems. If we want to categorize these two items, the first one is market participants that have benefit for owner of energy storage, and the second one is system operation benefit that will have benefit for system operators. Market benefit will be get benefit for the owner of the energy storage by difference between the high and low price in electricity market, and also the system operator benefit will be come by increasing the frequency response of energy storage, also increasing the virtual inertia of the network by more equipped facility and equipment. But there is a conflict between these two benefits. The first one is the electricity price and benefit for owner of energy storage. They need to inject power in the peak load demand and also absorb energy from the network in light load condition. But system operators need to inject power after an event in the power system that it means maybe it happened in light load conditions. So in this case, the benefit will lose, and there is a loss opportunity for energy storage owner. That is a conflict between system operator and also owner of the energy storage. To resolve this challenge, there is a lot of considerable solution that can be considered. The first one is integration of multi-objective optimization, multi-layer market participant, target incentive design, and advanced forecasting method can be considered to resolve this issue. The first one is considering both economic and also technical benefit for energy storage that should be considered in one optimization solution. If we consider economic as a one direction and technical benefit in another direction, it is a Pareto front that increasing technical benefit will reduce the economic benefit of owner and vice versa. But if we can implement some mechanism that have both benefit in line in one direction, it will increase network reliability and benefit of the owner of energy storage and will help the system operators. To do this, there's different market mechanisms that can be considered. For example, day-ahead and intraday energy markets, real-time balancing market, frequency response, and fast reserve and capacity and reliability markets. That if we have an opportunity to participate in energy storage in this market, it will increase the benefit. Other mechanism that can be considered for improving the benefit of owner is a regulative and incentive design for increasing the benefit, for example, stability adders, location specification period, premiums, and also reliability revenue that can be considered for energy storage. Also, another solution is a more accurate forecast method for renewables and also price markets. In order to resolve this issue, we should do a market redesign. Also, we should enhance the technology integration of the renewable to increase grid stability, and also we should have a price alignment in both directions to resolve this issue. In all other countries, Australia is the lead of countries for energy storage installation and also energy storage market that consider efficiency losses, opportunity cost losses for battery energy storage, and also frequency coefficient essential system services. Also frequency performance payment considered for energy storage in this market, but some other countries like UK, Ireland, Nordic country, United States and Canada just consider balancing market to participate energy storage in this network. You can see here a graph that we have techno-economic ancillary services market just for Australia, United States, and some European countries. Also, the yellow one shows the countries that just consider technical ancillary service markets, and the blue one is countries that just consider economic ancillary services market. And this pie chart shows the benefit for energy storage in Australia that mainly 65% are comprised from energy revenue that consider for energy storages. Considering ancillary services market in Australia show that if we have also energy benefit and also ancillary services market. It will increase 1 to 2% benefit of energy storage. Also, if we want to have more benefit from energy storages, we should have some investment on this equipment to have a faster response from the energy storages, named enhanced frequency response. Also, we need primary frequency response. That if we want to have this equipped, we should have some investment, and it will have cost for owner of the energy storage. If we want to use this facility, we need to compensate this cost for them. On the other side, we have a conflict between the freedom of the energy storage owner and also system operators. System operators need more controllability and more monitoring for energy storages. In the other hand, owner of the energy storage need more freedom to action to buy and sell electricity. If we want to have a better work and cooperation between system operator and also owner of energy storage, we should have a recursive process to make policy for this operation. If I want to sum up this presentation, there is a rapid growth for renewable energy resources and faces a power network with more challenges. To resolve this challenge, we need to have energy storage as a one solution, and to motivate owner and investor of energy storages, we should consider some market redesign, some regulatory framework, and some opportunity for them to participate in grid balancing and network reliability improvement and gain benefit from their energy storage. Thank you.
Thank you, Ali, for your presentation, and I would like to ask all the speakers to come to the stage and take your seating for the panel discussion. As we have a very limited time for the panels, we'll try. She's saying only 2 minutes for panel discussion. Can you believe that? Okay. So please, in order, so we can go one by one. I have prepared some of the questions based on your presentations, and please feel free if you have any question to raise your hand and participate in the panels. We'll start with Frederick. You did an excellent comparison of insulators. So in summary, can you give us what are the key challenges and when you're testing the insulators for severe environmental condition, and how your solution will enhance the grid resilience?
Yes. The key challenging to meet the requirement is polluted environment. It's now the coating. But it's the ultimate solution. Before, you need the insulator, proper design of the insulator string, and now the challenge is on the coating.
Hot. The challenge is
on the coating, sorry.
On the coating, okay.
Because up to date, we were in a situation where we had on one side the insulator manufacturer itself, coating material supplier, and the applicator. And now the challenge is to combine these three components in one final product, a complete solution, the requirements versus pollution.
Okay, so in GCC, we suffer a lot from high humidity.
GCC is well known to be a leader in this challenge, I would say.
Okay.
GCC is using a factory-coated insulator for a while now. And from our experience in the region, GCC is the leader in this, this new trend.
Okay, thank you. So, Engineer Abdullah, what are the primary factors driving Oman investment in transmission infrastructure, especially for renewable energy? Again, what are the primary factors for driving Oman infrastructure investment for renewable energy?
The primary to meet Oman target, where we have to maintain 40% in 2040, 30% in 2030. And we need to also have a diversity of generation from different perspective in terms of wind, solar. Having this share of renewable energy will take a lot of investment needed to be taken into consideration.
So in your presentation, I saw that by 2030 you will reach like 8 gigawatt or something like this.
Almost
renewable-
30%. 30% of
60%.
the total.
Do you know what are the annual growth of energy in Oman currently from year to year? And is it will it-
Mainly in coming years, the main dominant load, which is the direct customer, where we have industries. So to meet that demand, we need to invest a lot of.
Okay, thank you. Mr. Carr, based on your presentation, I have seen the renewable energy integration. What strategies can utilities adopt to accelerate renewable energy integration while maintaining grid stability? We can see all in GCC region, all member states, they are investing a lot in penetration of renewable energy, but how do we maintain the grid stability at the same time? If you can elaborate on this.
Yeah, sure. So we understand the complexity of upgrading this infrastructure. So the first thing first, there are 4 levers which has to work together. The society, the economics, like Mr. Ali explained, the technology stability, like Mr. Mohammed explained, and the technology. And coming from a technology perspective, we have to start with the basic maturity evaluation of every system. We have to start thinking bottom up, how we modernize, and then we have to think of the integrated planning for future. What do we need by 2030 or by 2050? And that has to be incorporated in the planning side.
Okay.
That is how there has to be a systematic and strategic leadership approach to this challenge.
Okay, thank you. Mr. Tata, so what are the latest technologies advancement in reactive power compensation that support the future growth of power grids? Do you have any clue about that? You can.
Yeah. So there are a lot of technologies available, like it depends upon the nature of the problem or kind of integration you are looking forward. So different grids or the different parts of a country or the different parts of the world will have different solutions for this. So if you have more and more renewables, then it can be like you are having more requirement for a reactive power, then you can go for a shunt reactor, variable shunt reactor, which I presented. Then there are some advanced technologies available like a STATCOM. It all are available and what kind of challenges you are facing in the grid and what kind of capital investment you are preparing for. So for easy solution, if you have a simple transmission line with a lot of capacitance and you need just a compensation for the reactive power, a shunt reactor or variable shunt reactor is sufficient because that will give you an easy solution, a simple solution without much complexity, and it will put a less burden on your pocket. But if you want to have more complex solution, when you want to integrate multiple back and forth on the renewables, you need to have more advanced systems like a STATCOM. Of course, it will call for a lot of capital expenditure, more complex grid, and it will have for some maintenance and subsequent activities which you do once you integrate all these things in the grid. It all depends upon the nature of problem and the modification which are readily available to do in the grid.
Okay, okay, thank you. Well done, well stated. Dr. Maximilian and Timo, a joint question. So what are the biggest geotechnical challenge faced during large-scale projects like your company? Do you have any clue about large geotechnical?
Okay. I try to answer this one for you. Well, in terms of geotechnics, there's always underground, and depending on the geology, you don't know what you have to drill through, but that's why there's always ground investigations in advance to address these problems we face in the ground. And once serious and adequate investigation is done beforehand, the risks and the challenges are reduced. And mostly from a geotechnical point of view, there's the groundwater table and changes in the mechanical behavior of rocks which, provide sometimes problems.
So how do we mitigate these associated risks? Is there any mitigation way?
I try to analyze the most risks ahead. So the most difficult situation or the most problems we face is to obtaining our building permits from the Bundesnetzagentur, also the permission to allow to build this kind of power lines through Germany, and of course to obtain the NOC from private owner of land.
Okay, thank you. Dr. Ali, now you have talked about renewable energy and also electricity, energy storage. So how can energy storage system be optimized to enhance grid stability? In summary.
Yes, as I mentioned in my presentation, there is some new facility that can enhance frequency response of the energy storages. If you can use this enhanced frequency response, it will increase also inertia of network, the increased penetration of renewable. Inertia of network will decrease and nadir point will be changed. So in order to enhance grid stability, new technology that have a response for frequency change will facilitate frequency response and enhance network reliability.
Okay, thank you. I'll open the question if anyone would like to raise a question. Mic there, please.
Assalamu alaikum, Mazen Shidani from PDO. If you allow me, Engineer Zahrani, I have two questions.
Please.
Okay, the first question, great presentation, Dr. Maximilian. You have mentioned that you have the power generation at the north-south of Germany and you need to give it to the demand, which is at the southern part, by using the underground cables. So my question here is there any strategy in place to monitor the environmental impact of the using of this underground cables over the time?
You mean whether there are any experience from the long term, how these cables behave and
Correct,
how they...
yeah.
Well,
environmental-wise, yeah.
Well, we have started to build and to plan these projects in Germany, and the first project we are part of is just about to be finished, and there's another one which is called Southeast Link, which is also almost ready to transmit energy, and a part of these there is no long-term experience right now. It's just based on the lab and upscaling from that.
I might to add in this one, as we know, we will face some issue with the transportation. That's why we implement to build two trenches in order to be able to repair one when other ones fall.
Okay.
So we try to ensure a continuously power supply to the people.
Thank you, thank you. Maybe my second question goes to Mr. Carr. Great presentation. You mentioned how we transit from the conventional grid up to autonomous grid. So in terms of cost, how do you see that autonomous grids compare to traditional grids when considering long-term benefits versus the initial investment? Also by take into consideration the cyber attacks and all of this. Yeah, that's all.
I mean, if the question is about how we compare the conventional grids that we have right now with the long-term grids that we are talking about? Is that the correct question? Well, first thing first, before comparing, it's a mandate now. We have to switch towards it. Second thing about your investment perspective, that's a very good question. The condition currently is that we are analyzing current situation and we are planning our investment based on what is urgently required. But the planning horizon has to expand to look at the return on investment. And considerations which has to come is also the volatility or the cost of lost power or cost of additional sources. Now this economics will decide how you start investing on your grid, when, where, and how. So the dynamics will definitely work in favor of, as per different reports which say, for every country, the investment when planned on these scenarios actually has given better development. And it's not just the power supply, it's about the entire economics of a country. So we have to look at a bigger horizon of investment and a bigger perspective of investment to do this evaluation.
Thank you. We have one
We
more
have
question
one
there.
more question. One last question.
Assalamu alaikum. I'm Hilal Al Hadi from Namad Distribution Company. We are responsible about renewable, small scale, below 25 megawatt. Actually, my question to Tata, Mr. Tata, actually regarding the stability of these small scale renewable systems, also including the EVs. Of course, for Oman, still we are scattered systems, but also we are thinking future, maybe these problems will happen. So from your experience, please, how to maybe think from now to mitigate such issues can happen in Oman distribution networks? Thank you.
Thanks for the question. From what I understood is you're talking about integration of renewables to a distribution network. Like when you have integration of large-scale renewables, it will be on the generation side and it can pose problems like this reactive power compensation and grid stability. But when you talk about small or what is a decentralized renewable sources, it can also pose a challenge of voltage stability at distribution grid. So we have some solutions like we call it line voltage regulator or some transformers which are with having a small OLTC. So these can have, because there is no challenge of any reactive power compensation because the distribution system will not be very long. So there you will face problem with a simple regulation. If you are moving away from the transformers, then you can have the voltage drop simply because of the regulation. Then we can have solutions called line voltage regulator, which can simply keep on boosting the voltage whenever there is less demand. Because the generation from the decentralized renewable source is not constant. It keep on varying, and sometimes the load can be very high and the generation can be very low. So in those cases, you can have either higher voltage, over voltage, or under voltage. So these solutions like this buck boost arrangement of transformers or the line voltage regulator we call it, they can control both over voltage and under voltage, keeping the distribution grid under stable condition.
Thank you very much for your excellent contribution, and thanks to all our speakers for your excellent presentations. We don't have any more time for any additional questions, but thank you. Looking forward for a second engagement in the future in IEEE. So that's the end of this session. Thank you very much.
1 second before we conclude, we just would like to hand a small certificate of appreciation to our speakers. So if you allow me, I would like to start with Mr. Frederick. Mohandas Hashim, if you would hand him the trophy, please, the certificate, please. The second certificate to Mr. Abhishek Kar. Apologies for this, it is for Mr. Abdullah Al-Habsi. The next one is Mr. Abhishek Kar. And Mr. Kilian Tata. Dr. Maximilian Sundel and Mr. Timo Geiger. And finally, Mr. Ali Kandani. At the end, I would like to invite Dr. Ahmed Al-Shakhsi to the stage to hand a small trophy of appreciation to our moderator, Mohandas Hashim Zahrani. Shukran Jazilan. Thank you so much, Bashmundis Hashim. It was a pleasure having you here. Thank you for all our speakers. We would like to have a group photo, if you don't mind, if you can please come to the front. Dr. Ahmed. And by this, we reach to the conclusion of this session. We will break now for lunch, and we'll be back for our last session of the day, which will focus on distribution networks. Thank you so much for your patience. Thank you for being here with us today, and we look forward to having you after the lunch. Thank you.